Welcome back. In the last lecture, we posed ourselves a problem that how to reconstruct a function on R 3 from the data given by the slices. That means, I have what we are going to have is that we have the average over all the planes of the function and we want to reconstruct the function. So, mathematically what we would like to say is that if P is a plane in R 3, we define Radon transform R f, where our f is a function in R 3 is a Schwarz class function we can take, is defined by R f. This is going to be a functional set of planes P. This we like to define P of f, that is the average of the function over the planes. Now, the first thing what we need to discuss, that what do we mean by integration over a plane P. Okay, so, now any plane is going to determine by a vector on the unit sphere, that is gives the direction and distance from the origin. So, we can define let gamma is in S 2, S 2 is the unit sphere in R 3. So, this is in R 3 such that x square plus y square plus z square, this is equal to 1. And then you take t belongs to R, then the plane which depends on t and this gamma, this is equal to all set of all x belongs to R 3 such that x dot gamma, this is at a distance t. So, the unit vector is orthogonal to it and distance t from the origin. So, easily one can see that P of t gamma, this is equal to P of minus t of minus of gamma, this is by definition. Now, how does one represent write down the element in this point in this plane? Now, choose E 1 and E 2 such that gamma E 1 and E 2 their orthonormal basis for R 3. That means, they are lying on the unit sphere and each of them they are mutually orthogonal, their dot product is 0. So, now if I take x in P t gamma, then this is going to be x can be written as t gamma plus u 1 e 1 plus u 2 e 2. Now, for f in Schwarz space of R 3, we define integral p over a plane P t gamma f, this to be equal to integral over R 2 f of T gamma plus u1 e1 plus u2 e2, then this is u1 and u2 are scalar variable d u1 and d u2. That is the basically the integral Riemann integration defined on R2 with each fixed t and gamma. So, this is what we mean by the integration over the plane of a function on R2. Okay, so far so good. So, now we have defined this, but what why should we believe that this is independent of the choice of the basis what we are taking. So, suppose someone is taking, suppose this is my gamma and someone is taking E1 and E2 here, somebody else can also take some E1 prime and E2 prime. Then why this integral over this Pt gamma is going to be the same for any or choice of the orthonormal basis. So, which we need to show that it is independent of the choice of basis. So, integral is independent with the choice of basis. Okay, let gamma E1 prime E2 prime be an orthonormal basis for R3. Then we can find a rotation R which is going to take my E1 to E1 prime and E2 to E2 prime. So, consider rotation R such that R of E1 is equal to E1 prime and R of E2 is equal to E2 prime. And therefore, if U is equal to U1 E1 plus U2 E2, then we denote RU, this is equal to U prime. So, now if we write down, then that is a trivial f of T gamma plus U1 prime E1 prime plus U2 prime E2 prime d U1 prime d U2 prime. This we can write the abuse of notation f of T gamma, this is R of U, and then this is d U1 prime d U2 prime. Make a change a variable. So, what you are going to get, this is R2 f of T gamma plus U, and then this is du, which is du U1 into du 2. So, this is independent of the choice of the basis. One of the interesting observation for this, what one can see is the following. Now, I want to claim integral over R3 of f of x dx, this is equal to integral minus infinity to infinity integral over p t gamma f dt. Now, x in R3 is through the standard basis, x is equal to x1 1 0 0 plus x2 0 1 0 and x3 of 0 0 1. So, what get the rotation r such that r of 1 0 0 is equal to gamma, r of 0 1 0 is equal to E 1, r of 0 0 1 this is equal to E 2. Then this is also going to be an orthonormal basis gamma E 1 and E 2, and therefore, what we do is that if we write integral over R 3 f of x dx, this is equal to integral over R 3 f of R x, and what I will get, again the Jacobian is determinant is mod of the determinant is 1. So, therefore, what we get this by the change of variable, and this if we rewrite, this is going to be f of x 1 gamma plus x 2 E 1 plus x 3 E 2, and then this is going to be dx 1 dx 2 dx 3. So, now this minus infinity to infinity, this is integral over R 2 f of x 1 gamma plus x 2 E 1 plus x 2 x 3 E 2 dx 2 dx 3 and then dx 1. This is nothing but minus infinity to infinity. This is what we have defined x 1 of gamma over f and then dx 1. This is with the same, to be consistent with our notation, this is p t gamma f dt, that is what we. So, this is going to be a very useful observation for us. So, now another thing what we would like to observe is that this Radon transform R f, this is a map on set of planes. Now, plane are determined by t and gamma. So, in other words, I can think for a given function f in the Schwarz space, R f is a map from R cross S 2 to C. So, we can consider R f a function on R cross unit sphere, that is S 2, because it is determined every plane is, we can write it in terms of the p t gamma for a fixed vector gamma and t. So, R f can be thought of this. So, now this is nice. At this point one can define the Schwarz space of R cross S 2. This is the function which is a function on t and gamma such that supremum over t belongs to R and gamma belongs to S 2 mod of t to the power k dl by dt L f of t gamma, this is finite. So, this is what is the Schwarz space, we can define this. Okay. So, now what is our goal? We want to reconstruct. So, goal want to reconstruct f from Radon transform. That is what we want to get, and so an easier question would be if for two functions f and g, if the Radon transform what we are getting the image is same, is it necessarily true that f is equal to g? That is the first thing. So, now that is what in mathematically we say uniqueness. If R f is equal to R g, then f is equal to g. Is it true? Second thing is that the reconstruction problem, that is the reconstruction, which we say that can f be expressed in terms of R f. Can we have a formula by knowing R f we can determine our f? That is what is the two main questions. So, we would like to address. Now, for the uniqueness, what we know is that from our Fourier analysis knowledge, that if f hat is equal to g hat for all points in R 3, then by inversion we know that f is going to be equal to g. So, that suggests us to look at convert this problem into the Fourier analysis problem and try to solve it. So, now remember that R f is a function on R cross S 2. Now, for each gamma belongs to S 2, each fixed gamma, R f dot gamma is a function on R. So, now we can talk of the Fourier transform of this function for each fixed gamma, provided if f is in Schwarz space, R f has to be integrable, Riemann integrable, having some moderate decay, then we can talk of the Fourier transform. So, that is the first thing we will see. So, let us write a proposition. If f is in Schwarz space of R 3, then for each fixed gamma in S 2, R f dot gamma, which is a function on R, belongs to the Schwarz space of R. Therefore, I can talk about the R f hat at xi gamma for fixed this is equal to f hat of xi gamma. Remember that this f hat is 3-dimensional Fourier transform. and this Fourier transform is one dimensional Fourier transform. And moreover, this actually one can write that R f, to avoid confusion, xi comma gamma, this is equal to integral over R f of t comma gamma e to the power minus 2 pi I xi dot xi t. Here this is the both xi and t are in R, then this is dt, and f hat of xi gamma, this is equal to integral over R 3 f of x e to the power minus 2 pi I xi gamma dot x dx. So, that is the 3 dimensional Fourier transform what we are talking about. So, now first to prove that this R f for each fixed gamma, we would like to show that R f Radon transform is a source class function on R. So, now what do we know? We know that f given to us, that f is in the source space. Therefore, 1 plus mod t to the power n, 1 plus mod u to the power n, mod of f of t gamma plus u, this supremum is lesser equal to a n, and also its derivative. So, therefore, when we are writing that in order to show that R f is a source class function, we need to show that R f t comma gamma, this is lesser equal to some supremum over t, is less than finite. That is what we want to show. This is what we want. Now, what is my, let us write 1 plus mod t to the power n R f of t comma gamma, this is lesser equal to, or rather one more step, 1 plus mod t to the power n, and this is R 2 f of t gamma plus u du. Now, if I take the mod, then I have mod over here, which is lesser equal to 1 plus mod t to the power n, and then this is integral R 2. This is definitely lesser equal to some constant a n by 1 plus mod u to the power n, 1 plus mod t to the power n and du, because f is in the source space of R n, that is what we have seen. So, now this is lesser equal to a n du by 1 plus mod u to the power n, and for large n. So, this is finite, which is independent of u. Okay. So, therefore, and exactly the same kind of argument we can give for the derivative with respect to t. So, we can get that actually R f, hence R f dot gamma, this belongs to the source space of R. So, now what we would like to then find out, R f hat at xi comma gamma, this is equal to integral minus infinity to infinity. Now, this is RF is integral over p over the plane p t gamma f, then e to the power minus 2 pi I xi t dt. Okay. So, now as you can see that the t I can write this, I can write this as t gamma dot, or this is gamma dot t gamma plus u. Remember that u is E1, E1, E2, there U2, E2, they are basically the gamma E1, E2 are the orthonormal basis. Therefore, this gamma dot gamma is 1, this is the unit vector. So, this is just gives me t because gamma dot u is 0. So, now this I can represent it minus infinity to infinity, this is p t gamma f, and then this I can replace minus 2 pi I xi t, in place of t we can write t gamma plus u. I can put this as inside now, this d, this is, and then this is dt. This all we had the observation that this is going to be R 3 f of x e to the power minus 2 pi I xi gamma dot x dx, and this is nothing but the Fourier transform of xi into gamma. Xi is a scalar. So, once we have that, as you can easily one can see a corollary, if R f is equal to R g, then f is equal to g. The proof is same because this is R f of t R f hat at xi comma gamma, this is equal to R g hat at xi comma gamma. This implies that f hat Fourier transform in 3 dimensional xi gamma is equal to g hat of xi gamma. Now, this is true for each gamma varies over the sphere S2 unit sphere, and this is true for all the all xi in R, for all xi in R. And now, we can vary this, I fix a gamma, then I will get that f hat of xi gamma equal to g hat of xi gamma. So, similarly, I will vary another gamma, every gamma on the sphere, then I am going to get this. So, this implies, because if I take any x in R 3, then this is going to be given to me a direction and the distance from the origin, that means some xi and gamma x equal to xi dot gamma. So, this implies f hat of x is equal to g hat of x for all x in R 3. So, by uniqueness of the Fourier transform, this will imply that f is equal to g. So, this gives us the solution of the uniqueness problem what we have posed, that if two data they agree, whatever the data we are getting, if they agree, then the original function, both the functions has to be equal. So, in the next lecture, we will try to find a formula to reconstruct our f from the given data of the Radon transform. Thank you.